Welcome back with another video of equivalent series. Today we will be seeing how equivalent resistivity is solved. In the last video I discussed about equivalent resistance. Now in this video I'm going to talk about equivalent resistivity. Right, what is resistivity? The theory part involved here is this. Resistivity is defined as this. The basic equation is R equals rho L over A. Resistance is defined as rho L over A. So resistivity is RA over L. Resistivity is RA over L. Resistivity is a property which is in the material or in the substance of the conductor. Got it? Resistivity. So in this equation, this is resistance. This is how the equation is. This is resistance. Resistance. And rho is resistivity. Resistivity is a constant for a given substance. Resistivity. L, length. This is cross-sectional area. Right? So basically, this refers to this kind of a conductor. This kind of a conductor. See? This kind of a conductor material of cross-sectional area A, length L, and resistivity rho. Resistance of this conductor can be written as rho L over A. This is the basic idea. Right? Now let's see how equivalent resistivity is solved when conductors are connected in series and parallel combinations. Right? First, let's see the series combination. Series combination. See. Series combination. Right. I'm going to consider two rods which are connected in series combination. Two conductor rods. Two conductor rods connected in series combination. Let's say length of each rod is L. Length of each rod is L. And area of each rod is A. Right? Then the equivalent to replace this system should be, because we know equivalent should fulfill the same gap the system was there before. Right? The purpose of equivalent is that replacing the system, and always equivalent should undergo all the things the system when there is on the system, when there is in the system. Doesn't matter how many number of rods are there, conductor rods are there, right? The same thing happened for the system should be done for the single equivalent single-handedly, right? Solely. That's the idea. So therefore, this should fit the gap between these two. This should fit this gap. This should fit the gap. Therefore, length of the equivalent should be 2L. Length of the equivalent should be 2L. And area is same A, because it should fit the same gap. It should fit into the same gap. Got it? Okay. Now let's consider the current capital I flows through this system. A current capital I flows. So we know if there are no junctions, current is not going to be divided. If there are no junctions, therefore, same I flows through this conductor rod, through this one, and it goes out. If there is same I, same throughout, same I should be flowed through the equivalent as well. Same I should be flowed through the equivalent as well. Same I. Right. Now, let's consider their resistivities as rho 1, rho 2, and rho E. Resistivities. Now we are interested about resistivities, right? But in the previous video, I proved what happens with equivalent resistance. Now we are going to use that same idea we had in equivalent resistance and going to make use of that proved equation to get something here, to get an equation here, right? Now, if there is a conductor rod, we know as equivalent spring, as equivalent resistance, it should have equivalent resistivity as well, right? Resistivity and resistance both should be there, because according to the equation R equals rho L over A, if there's a resistivity, there's a resistance. Or other way, if there's a resistance, there's a resistivity. Therefore, for these conductor rods, there should be a resistance as well. Now I'm going to consider that respective resistances as R1, R2, and Re. So let's consider resistance of this one as R1, resistance of this one as Re, resistance of the equivalent as R2, and resistance of the equivalent as Re. Now, if I think of the resistance here, resistance again with Rakidano, resistance again with Rakidan. For this conductor rod, it has a resistance. See, for this conductor rod, it has a resistance like this. And for this conductor rod also, it has a resistance like this. Right? Now, if these two resistors are R1 and R2, these two are in a series combination. So we know in series combination, we know how to simplify resistance from the previous idea. Right? We know how to simplify resistance. We are going to use that idea. Then what I can say is Re equals resistance, Re equals R1 plus R2, isn't it? Re should be R1 plus R2 because these two resistors are in series combination. Now we know R equals rho L over A. See how the idea is transformed into resistivity. So R equals rho L over A. R equals rho L over A. Simplify this. Expand these terms. Re. Rho is rho E. L for equivalent is 2L over A. Right? Equals R1 rho 1 L over A plus R2 rho 2 L over A. Right? L2, L cancels, A2, A cancels. What comes here? 2 rho E equals rho 1 plus rho 2. Then rho E equals rho 1 plus rho 2 over 2. Rho 1 plus rho 2 over 2. This is the proved equation for equivalent resistivity in series combination. Right? This is only for 2 rods. If you need 3 rods, 3 conducting rods, you have to do this again and get it done. So what comes here is if the lengths are equal, what comes is rho 1 plus rho 2 plus rho 3 over 3. But if lengths are different, also you can do the calculation, right? Even though lengths are different, that is just fine. That is just fine. If the lengths are L1 and L2, the equivalent length is going to be L1 plus L2. So likewise, if lengths are different also, you can still do the same. Then length won't be cancelled, but still we can find the equivalent resistivity, right? So I considered here the equal lengths for the ease of simplification. Otherwise, for the different lengths also still you can do. So you give it a try and put a comment whether you got the answer with the different lengths. Right. Now series combination is done. Now let's see what happens in parallel combination. Right. Same approach. Now parallel combination. Parallel combination of rods. See. Parallel combination. Right. Now let's consider two rods which are connected parallelly like this. Right. And let's consider area of each as A and length as L. Equivalent should replace the same gap. Right. Then area of the equivalent should be, to replace the same gap, area of the equivalent should be 2A because total area, the net area we had in the system before is 2A. In the equivalent, it should be having 2A single-handedly. So this is 2A, but length is same L. Length is same L. Right. So let's consider their resistivities as rho 1 and rho 2 and rho E, and their resistances as R1, R2 and RE. Resistivities as rho 1, rho 2, rho 3 and resistances as R1, R2, RE as before. Right. Now let's consider the current flows through the system as I. Right. Current flows through the system as I. Right. Now we know right here, if resistors are R1, R2, now this is just like two resistors in parallel combination. This is just like two resistors in parallel combination. So we know in parallel combination currents are different. But we have proved, considering that different currents, we have proved an equation for resistance in the previous video. Now again we are going to reuse that idea, right? If these resistors are R1 and R2 in parallel combination, we know equivalent resistance Re comes as 1 over Re equals 1 over R1 plus 1 over R2. 1 over Re equals 1 over R1 plus 1 over R2. right? Then we can convert this idea to resistivity because we know R equals rho L over A. R equals rho L over A. So plug it. 1 over RE, then 1 over R will be A over rho L. No? Is it clear? If R equals rho L over A, 1 over R is, right? 1 over R is, put both sides 1 over A over rho L. A over rho L. Right? 1 over R is A over rho L. Right? So directly, I'm going to plug that here. 1 over R is then 2A over rho E L. 1 over R1 is A over rho 1 L. And 1 over R2 is A over rho 2 L. Right? A cancels. L2, L cancels. 2 over rho E. Apply a common denominator here. Right? See, what remains here is 1 over rho 1 plus 1 over rho 2. Apply a common denominator here. That is rho 1, rho 2. Right? And here it is rho 1 plus rho 2. This side 2 over rho E. Subject rho E. Rho E is 2 rho 1 rho 2 over rho 1 plus rho 2. This is called equivalent resistivity in parallel combination, right? 2 rho 1 rho 2 over rho 1 plus rho 2. If there are 3 rods, the equation is going to be different. So therefore, again, you have to do the calculation. The equation is going to be different as 3 rho 1 rho 2 rho 3 over rho 1 rho 2 plus rho 2 rho 3 plus rho 1 rho 3. Simplify and see and put a comment if you were able to do it. If the for 3 rods, right? Okay, this is for 2 rods, right? I have wrote it for 2 rods. This is the equivalent resistivity for parallel combination, right? Okay. So hope it's clear, right? Hope it's clear. If there's any questions, you can put a comment, then I can see. Right. Now I'm going to stop the video here. See you all in the next video of equivalent series. Goodbye.